So the shrimp works on producing ions, and these are charged particles. So we start off with atoms, we remove an electron, we add an electron, and we end up with a charged particle called an ion. And the neat thing about ions is you can accelerate them just in simple electric fields. So we keep our instruments at high vacuum so that the nature of the charge doesn't get taken away and get wiped out on a gas atom or something like that from our atmosphere. So we spent a lot of time keeping these instruments at vacuum and at fairly high vacuum. So you may have heard the story that nature abhors a vacuum. Demonstrably, nature does not abhor a vacuum. The universe is mostly vacuum. Nature abhors a vacuum pump. So we spend most of our time fixing vacuum pumps, fixing electrical boards so that we can manipulate those ions that we have. So the shrimps are known as secondary ion mass spectrometers. They produce an ion beam off a sample, off a target, and we use a primary ion beam to actually excite those secondary ions away from the target. So there is an energetic primary beam of oxygen or cesium, and the oxygen and cesium themselves are ionized, so there's usually an O2 minus beam and a cesium plus beam, and these are accelerated to 15 kilovolts down onto the target, and this is enough energy to actually physically erode or ablate. And we can see some pits here on the screen that have been, this is one of our standard materials, so it's got lots of holes in it, looks a bit like Swiss cheese, and these are the pits that we actually ablate. So we can put a sample into the microscope and focus in on it, and then we can burn a spot on the actual target material that we're after. And we can see it burning, we can see effectively that primary ion beam interaction, and then we're taking off through the interaction of that primary beam, because it's so energetic, it's also causing the target atoms to be ablated away, but also to vibrate extremely strongly so that they will lose an electron, or if there's enough electrons around the cloud, they may gain an electron as well. So there's a lot going on. It's a very complicated process, and nobody really knows exactly what's going on. We don't model it particularly well, but we're just using it. So we measure a lot of standard materials. So we say, okay, our standard is going to behave exactly the same as our unknown materials, and so we match them up mineralogically and make sure that our target looks very similar to what our unknowns are as well. So we can sort of use that as a constant between them, and then just back out what the composition of our unknown material is. So the shrimps were designed and constructed in RSES starting in about the late 1970s, and it was to fulfill a need to be able to do isotopic analysis on in situ, on grains and solid materials that we could actually mount up and put into mounts, such as what we have in this tray. And those solid materials are then ablated by a primary ion beam. Typically for these instruments we use either oxygen or cesium. So the oxygen beam we use for analysing metals, for the cesium we use for analysing non-metals. The metals we analyse as positive ions, the non-metals we analyse as negative ions. So we have these configurations. It's all straightforward electrical configuration for the instruments, which allows us to accelerate the ions from the surface. These are the secondary ions, so the sample's been ablated. A small fraction of the material that comes off gets ionised, and that gets drawn out through the mass spectrometer of the shrimps. So the shrimps, it's an interesting descriptor, because the shrimps are obviously quite large. They're not small instruments at all, and one of the frequent questions is, why is shrimp so big? And it's big because we need to do two things. One is we need quite high mass resolution to be able to separate molecules which will interfere with the species we're after. And the second thing we're after is to be able to keep as many of the ions that are coming off the surface of the target through to the other end of the mass spectrometer. So that gives us our sensitivity, and of course the sensitivity is what gives part of its name, sensitive high resolution ion microprobe. So the mass spectrometer is about 7 meters in length, the magnet turning radius is 1 meter. and those were almost an order of magnitude larger than any instrument at the time. So the shrimp name is sort of a bit of a play on words related to the fact that shrimp is usually small in Australia, but in this case it is rather large. So it's one of those things, we designed it to be as big as possible to give us the best possible outcomes. So we're using those ions as effectively a sample of the target, and so whatever isotopic compositions we can measure out of the targets come back in terms of what we're going to portray as the actual isotopic composition of the material. So it's sort of the difference between atoms in a solid material versus what we're ablating and what we're seeing as ions. So we just figure there's some sort of functional relationship between the ions we get off the target and what's actually in the sample itself. So that's the main crux, and that's why we need to measure standards, that we need to know how this material is going to behave under that ion beam, and also to then condition our response to the detectors and so forth, and how we measure these things. So within these materials we're trying to measure various compositions, and ion microprobes were originally constructed because you may have heard of electron microscopes and the ability of an electron beam to knock out a characteristic electron or one of the inner electrons in the orbit, and that generates an X-ray, and then we can measure the X-ray intensities as a proxy for elemental concentrations. So that's really well known. People have done that for years, and it's a very straightforward process. But it's like when part of the benefit of actually looking at the ion microprobe is that we can go to much lower concentrations. So the X-rays have lots of background issues with them, and so you can get percent levels of elemental concentrations. If we start looking at particle beams, we can get down to parts per million and even parts per billion within a target. So it just allows us to look at the concentrations of much lower concentration elements and back out exactly what concentrations they might be. So this is useful for understanding how igneous rocks form, how the trace elements partition between different mineral phases in those, in a granite for example, between feldspars and zircon or something like that. We can basically back out those concentrations and have an understanding of how that magma crystallized into a granitic rock that we can hold in our hands. So one of the key applications that was envisaged for Shrimp 1 when it was first built was to be able to target a mineral called zircon. And zircon contains a little bit of uranium but no lead, and so we can actually measure the uranium decay chain and measure lead, which the uranium decays to, and the uranium, and so that lead over uranium is actually a chronometer. We can actually solve the equations of radioactive decay and come up with an age of a specific zircon. So our standard here, this is known as SL13, this is a pebble that came from Sri Lanka, and we use that for standardizing analyses for quite a long time. It has 238 parts per million uranium and 20 parts per million thorium, and the uranium decays into, uranium-238 decays into lead-206, and uranium-235 decays into lead-207, and the thorium-232 decays into lead-208. So we can set up those three decay chains and actually solve the equations to actually determine an age for each one of those decay schemes. If they all behave, then we come up with an equal age, and if we're worried about one of them being dissimilar, then we're sort of worried about the whole ability of that single zircon grain to be able to act as a clock. So SL13 is 572 million years old, so all of our analyses can be normalized to one analysis of SL13, and we can back out, because from effectively what we have to do is from our iron ratios figure out what that means in terms of the absolute concentrations, because we need those to go into the decay equation, not strictly our iron ratios, because there's sort of different ionization probabilities for lead versus uranium, so that's where our standard comes in. So we know what we should get off this guy. If we apply the same filter to what we were doing to SL13, to our unknowns, then we can back out an age. And so uranium lead is one of the premier geochronometers. We can cover the full range of geological time, going from 4.56 billion years ago, which is the age of the solar system, so I've dated zircons from meteorites, all the way through to about 1 million years or even less when we start looking at very young rocks, such as some of the volcanics in New Zealand get very young. But we can even go lower than that, because there's some weird behavior. We're not actually looking at a direct uranium to lead decay. There's all these weird isotopes in between, because we need 8 alpha decays to get from 238 to 206 lead. And so there's 8 alphas there, and so there's all these little decay products in between. If we use those, we can actually figure out things down into the tens of thousands of years. And so this gives us ability effectively to cover the full range of geological time. So one of the first major applications where shrimp became well known internationally was the analysis of the oldest zircons on Earth. And these were found at Mount Narraya in Western Australia. It was a PhD project of a colleague of mine, Derek Frood, and he'd gone out to Western Australia and collected quartzites. And so the idea was that these quartzites would scavenge zircon grains from all over the place. And so if you analysed these quartzites, you would get a spectrum of zircons which might tell you about the history of that area. And so one of the key goals was to see, is there actually anything really old in Western Australia? We knew there were old rocks back to about 3.7 billion years, but if you start looking at sediments, maybe you'll find something which is preserved, which is quite a bit older. And so Derek brought these samples back, made up these epoxy mounts with lots of zircon grains in them, hundreds of zircon grains. And so this was one of the prime abilities of shrimp, was to actually go in and be able to analyse a single grain in 10-15 minutes or thereabouts and come up with an age. And so I remember this very well, because we were sitting in the lab, and Derek had been running overnight, or getting it going overnight. It wasn't running very well, but anyway, he handed it over to me to run during the day. And in those days we used to have chart recorders, and so these are sort of like little treadmill things which screed out pieces of paper and had little ink runners and pens that showed you what the compositions were. And so shrimp wasn't running very well that day. There was something wrong with the primary beam or something, and so it just wasn't going very well. But we hit zircon number 12 out of the sample, and this is the ability of measuring lead isotope compositions, because the 7.6 was over 0.5, and so everything in terms of terrestrial ages to that time, 3.8 billion years, has a 7.6 lead ratio of less than 0.4. So the fact that I could just look on this chart recorder, it's 0.6, it's like, whoa, this is really old. And so you can go and look on charts and you can recalculate, and that's about 4.1 billion years old. And so this is like 300 million years older than anything had ever been dated on Earth before. So that was very exciting, and Derek was very happy when he came back in that I'd found this zircon for him. And then we found about 4 more in that mount, and there's about 4 zircons in the Nature paper that came out. And so it was just a fantastic opportunity to actually see science in action, that you could actually just use a chart recorder to determine something as intricate as determining an age of a zircon grain. So that was fantastic. So then we found more zircons at Jack Hills, and so then this opens up this period of Earth history called the HADEAN, which is anything older than about 4 billion years. So effectively the HADEAN was discovered at RSES, and there's lots of people now all over the world looking for these HADEAN rocks and what it can tell you about Earth history. Now, as I said, these are all from quartzites. We don't actually have the rocks, and so there was a big effort then put into, can we find igneous rocks of that age? We haven't found any. And so the oldest rocks on the planet are still only about 4.0 billion years old. The oldest zircons we have out of the Western Australian rocks go back to about 4.35 billion years. And that's pretty amazing, because that's only 200 million years younger than the planet itself. So within 200 million years, the planet had crystallized, it had differentiated. We were getting something which was causing sediments maybe to subduct or go down, but we're not sure if plate tectonics was active at that time or not. But something was, we can get Earth history all the way back to that time. So that was a fantastic result out of the HADEAN zircons. So one of the key aspects of geochronology that the HADEAN work demonstrated was that you could take a sediment and then as a sample of how rocks actually interact and what their history is. So we're looking at the prehistory of a rock. The quartzites from Jack Hills are only about 3.1 billion years, but they're containing 4.3 billion year old zircon. So really important concept there of history preserved in these rocks. So we can use that in actually going to more modern rocks and using them for associations. And so one of the key things I was interested in, I'm a New Zealander, and so how does New Zealand relate to Australia and to Antarctica? And so there's this type of rock around all of the margins of Australia and New Zealand and Antarctica called GREYWACKE, which is basically just a chewed up granite and very primitive sediment. And so if you look at, and this is demonstrated to a certain extent when you look at things like road metals. So these GREYWACKEs actually produce very good road metal, and so you can sample these things quite easily if you wanted to get road metal. But you can go to the quarry, so we just use the quarry, so that's fine. But you can actually pull out the different histories. So on the west coast of New Zealand, there's a blue metal called the Greenland group. And we were able to break up those zircons and analyze them, get a spectrum of ages. And so this spectrum is really characteristic of Gondwana. It has a spike in age at about 500, then 1,000, and then a little bit of 1,500, 1,600, and then a dribble of ages all the way out to 3.5 billion years. Now, New Zealand's an offshore island. It doesn't have rocks of that age either. So this concept of where was it X 100 million years ago when all these things were going. Turns out that that signature is characteristic of the east coast of Australia. It's also characteristic of Western Antarctica. So all of these continents were linked together, and so you can see this if you look at the stitching of the associated with the spreading ridges and things like that, the magnetic stripes. You can pull them back together, and about 200 million years ago these were all reconnected and formed the single continent of Gondwana. So what we're looking at is basically just different aspects of the same rock unit. But we can go further than that. We can actually start looking at rocks which may be inboard of that in Australia. So we went over to the Adelaide Fold Belt and pull off the rocks there, and the Adelaide Fold Belt is meant to be the start of these rocks out on the east coast of Australia. But it turns out they're completely different. They have a completely different signature. They're mainly 600 to 800 million years old. They don't have the 500. They don't have that 1,000 peak. So they just look very different, and so that allows us to establish these connections between different aspects of geology simply by looking at a spectrum of zircon grains from a single rock. So I've been associated with the Hayabusa sample return missions for about the last 15 years. And so this was a concept developed by the Japanese Space Agency to go out to a near-Earth asteroid, land on the surface, grab a sample and bring it back to Earth. Nobody had ever done that before. And the Hayabusa 1 went out to a little asteroid 500 meters across and touched down and brought that sample home. Now, that sounds so simple, but it wasn't. There were all sorts of things went wrong, but the Japanese did a phenomenal job of actually solving all the problems that came about and to actually return that sample. And so the spacecraft went out on an orbit associated with the asteroid, which is going between Earth and Mars, and so you follow out the trajectory and the sampling, because you actually want to communicate with the spacecraft and also to have the solar energy on the panels to be able to power everything up. All of this was done on the other side of the solar system. So that's 70 light minutes return time. So remember, 8 minutes to the sun, out to Earth, same distance on the other side, another 8 minutes, so there's 16 minutes. And so you can't actually get this to operate by, okay, touchdown, grab a sample, come back. It's all got to be autonomous. And so there's a computer on the surface that's programmed, goes down to the surface. There was meant to be a bullet fired, stirs everything up, and sample goes up the sampler horn. Turns out the bullet didn't fire. Oh dear. But it did touch down, and so there's just in touching down, just on that, it's coming down at maybe 0.5 meter per second onto the sample, onto the asteroid. It touched down, and there's enough dust stirred up, got up the chamber, got isolated, contained, and we've got that. So we got about 1,500 grains of material which were curated and documented that we could analyse. And so just out of those 1,500 grains, we were able to establish that they have the same chemical composition as the LL group of chondrites. And so we're immediately able to match it to a meteorite family that we have here on Earth. We also found that the oxygen isotope compositions, remember we can use ion microprobes to analyse oxygen, the compositions that were measured from those grains were extraterrestrial. They don't look like terrestrial. There is some variations and isotope abundances that we can ascribe to extraterrestrial materials, and we're able to do that. So that verified that the samples that we contained actually were from that asteroid. And that was important because one of the key findings of that mission was that the surface of that asteroid had only been exposed to solar wind for only 8 million years, and that's million with an M. It's not billion, because we like looking at old things, but it was only 8 million, and this is blink of an eye in terms of solar system history. And so obviously this thing must have been disrupted at some stage, and then it's either been recycling when it came down into Earth orbit. We're not sure if it was exploded, had a big collision out in the asteroid belt and then assembled and migrated in, or how that worked, but we know it was very recent. And so this gives you a key understanding of what's going on in our solar system, because you're getting impacts of different objects out there in space, and they're sort of recycling material in space and they're bringing that down to Earth. Now we're also worried a little bit that those type of asteroids could come down onto Earth, and you may have seen some of those Bruce Willis movies about putting the stake on and jetting it out into another orbit. This is a rubble pile asteroid. We'd sort of conjectured these, but never actually seen one. So this is 500 meters across of just aggregate. It's like a shovel full of concrete pre-mix. But it's not solid. There's no water out there to actually solidify all this together. So if Bruce Willis was to go out there and stick a stake in the ground and pull away, you'd pull away maybe a few boulders, but you're not going to disrupt that asteroid. So it tells us something about how we're going to deal with an asteroid if it does get onto an Earth crossing orbit, and we need to get worried about what it's going to do to us. So end of last year, I went back out to Woomera to participate in the recovery of the Hayabusa 2 sample return capsule. So you would have seen this on the news that JAXA had got out to another asteroid, this time Ryugu, and touched down and grabbed a sample, and then shot a bullet into the surface, made an artificial crater. Then they went back down and sampled inside that crater and actually got fresh material. So we have the surface composition. This will give us the exposure ages that we had for ITOKAWA, so we know how long that asteroid has been exposed, but it also gives us that internal as maybe an idea of how this object has evolved. And so we think Ryugu's got a very different history, because if you look at some of the images of it, it looks like a diamond shape, and this has been rotating, so all the stuff has migrated from the poles and the flanks down onto that ridge, and so now you have this diamond shape spinning top type arrangement, and so we think it's going to be older. My bet is it's going to be older. We'll see, but we've got the samples now. So that was what I was out on Woomera for the retrieval of the sample capsule. flawless re-entry. We went out on the first thing in the morning and picked up this spacecraft. You don't do that every day. Came back into the lab and we sampled the gases, and so the gases were interesting because they show solar wind, they show helium. And so we only see helium in solar wind. We don't see helium that much on Earth. If we get helium, it generally just migrates out of the atmosphere. So there's not a lot of helium on Earth. The fact that we had helium tells us that it was extraterrestrial. And there's another nice story that while we were there, one of the journalists gave us a microphone to stick on the outside of the sample container, and then it was rotated and you could actually hear what was inside rattling round, and so we knew there was something good inside there. We couldn't tell anybody at that stage, but now it's been opened and we can see that gravelly material. It's black, and one of the key issues for the Ryugu mission, the Ryugu sampling, was to try and associate these dark asteroids, these dark C-type asteroids, with what we have in the meteorites, which are dark, which are the carbonaceous chondrites. And so one of the big issues is that carbonaceous chondrites are quite rare types of chondrites. We don't see very many of them. The C-type asteroids are the most common type of asteroids. So there's an enigma there as to the relationship between what we get as meteorites versus what's out there in terms of the asteroid belt. So if we have actually linked up the C-type asteroids with carbonaceous chondrites, we are going to give us a much better window into understanding how the carbonaceous chondrites were delivered to Earth. And that's important because these type of meteorites contain all of the organics, they contain water. Was that the seed of life on Earth? Were these organics, because we know there are simple amino acids in these meteorites, were they then reassembled as proteins that went on to form life? Did that water that was associated with carbonaceous chondrites form the oceans? So big questions about Earth history that are accessible now because we got these samples back from Ryugu. So one of the things we spend quite a lot of time doing is measuring stable isotope abundances, and all of the elements have isotope compositions which are reasonably stable on Earth, and so, or consistent I would say. But if you get to the light elements, various processes can fractionate these isotopes, and so one of the key things you can look at is the isotopic composition of oxygen as you go from the equator through to the poles. And the isotopic composition of oxygen gets very much lighter as you go to the poles because you're getting condensation, and the condensation as rain comes out from the equator takes out the heavy isotope, it condenses first, the light isotope keeps on flying away until it effectively gets to the pole. A little bit more complicated than that, but you get the picture that you leave the light isotope flying around. So if we go and measure ice cores from Greenland, these are being used as proxies for temperature and paleo temperature as we go back in Earth history. We can do the same sort of things either on carbonates. We can look at limestones, calcium carbonates, things like that, speleothems, looking at cave deposits, and then back out temperature histories and profiles that may be related to climate and to changes in climatic temperatures and various other processes which go along. We can also use those stable isotopes from our zircons to actually understand how they form. So one of the key things in terms of Earth's surface processes is the weathering of surfaces where you get enrichments in heavy isotopes and the concentrations of those heavy isotopes during various processes. And so if we see those going, if we effectively see that signature in a granite, it means you've had subduction or something like that. You've recycled surface material all the way underneath. We can also do that for diamonds. We can do carbon isotope compositions and see that some of the carbon in some of those rocks that we might measure, like obtaining diamonds from, actually have a crustal history, and we can see that in carbon isotopes, we can see it in nitrogen isotopes, we can actually see it in lead isotopes and inclusions as well. So all of these things are telling us about the history of Earth and how materials are cycled back and processed as they come back up to the surface and we start sampling these things. So a very powerful technique, understanding what the abundances of isotopes of different elemental systems tell you about the prehistory of rocks on Earth. So a similar sort of thing to looking for the Jack Hill zircons. We can go to a meteorite, which is a sample of the molecular cloud or the material which formed our solar system, and start trying to find grains which actually predate our solar system. And so what we're looking for is variability in these isotopic compositions, because it turns out different grains forming around different stars will come out with different isotope compositions. And these just aren't subtle variations. You know, we try to measure as accurately as possible on Earth, but we see orders of magnitude variation in carbon and nitrogen isotopes of various grains. And we're looking for carbon and nitrogen isotopes because, as it turns out, one of the best ways of finding these grains in a meteorite is to digest the meteorite with acid. And so it's like finding the needle in the haystack. First thing you do is burn down the haystack, get rid of the haystack, and then look for the needles that are left over. And so when we did this, we found things like silicon carbide, graphite, diamond grains. And so we went out and measured the isotope compositions of those grains. And most of those grains in silicon carbide land come from what are known as AGB stars, asymptotic giant branch stars. These are the red giants. So at the moment, if you look up in the sky, you'll see Orion. The big red star down the bottom is Betelgeuse. Next to it is Antares, another red giant star. So there's a lot of these red giants, and they're the smoky, they form these planetary nebulae as well. See these shells of dust coming out, and so these are the source of the dust which actually forms our solar system. So we can tell that a lot of the material which forming our solar system probably came through that pathway of another star. We know the elements have to be built in other stars. Out of the Big Bang, we only have hydrogen and helium. We need stellar nucleosynthesis to form carbon, nitrogen, and all the other elements that make up us and all the materials that we have around us, making up planetary objects. So we can. We also know that supernovae produce a lot of material that we can see as well. So we can see these grains, we can see their signatures and isotope compositions, and then tell everybody what actually happened before we started forming the solar system.